Okay, so here are a few more Chapter 7 review problems. So the first one is graph in a log. Then later on, it's evaluating a couple different log terms. And the last one will be one of those expansion type things. So the first one, graph in a log. All right. Now, the way we've been graphing logs is to not actually graph the log directly. It's to find the inverse first, if you remember. So the inverse is going to be x equals log base 2 of y minus 1 plus 2. So then I want to isolate the y. So if I subtract 2 first, equals log base 2 of y minus 1. And then at this point, I can use the log conversion formula. So I'll write it over here. That's if I have log base b of a equals c, that turns into b to the c equals a. So in this problem, the b, this b is 2. So I've got 2. And then the c that I need to raise the 2 to the power of is the thing that the log equals. So that's x minus 2. So 2 to the x minus 2 equals, and then the thing inside the log is a. So that's what it equals. So I'm going to put y minus 1 here. And then if I add the 1 over, I've got y equals 2 to the x minus 2 plus 1. So here's the inverse, right? This is the inverse. Okay, so what we can do is make a chart for the inverse. So the parent of the inverse is going to be y equals 2 to the x. And so if we make a chart of values for this, usually the values we've been using are -2, -1, 0, 1, and 2. And then 2 to the -2 is, so over here on the side, 2 to the -2 is 1 over 2 squared. So that's 1/4. 2 to the -1 is 1 over 2. Remember, 2 to the 0, anything to the 0 is going to be 1. 2 to the first is 2, and 2 squared is 4. And then you might remember, generally speaking, 2 to the x, or 3 to the x, or 4 to the x, they all look like this. So there's a domain of all real numbers. There's a range of everything that's positive. You can't actually get to 0, it approaches 0. And the asymptote there is y equals 0. Let me scroll down a little bit. Okay. So that's the first chart. And then what we're going to do is we want to manipulate this. So it's x minus 2, that's going to be 2 to the right, and then plus 1, so 1 up. So I'm going to have to add 2 to the x's and add 1 to the y's. All right, so then our new chart, x, y, this is going to be for y equals 2 to the x minus 2 plus 1. So let's see, that will be, what do we need here? 2 to the right. So I'm going to add 2 to all the x's, so instead of -2, it's 0, then 1, then 2, then 3, then 4. And add 1 to all the y's, so it's 1 and 1/4, 1 1/2, 2, 3, and 5. And then the domain, if I add 2 to all numbers, I still get all numbers. If I add 1 to the y's, then the new range is y is greater than 1, and the new asymptote will be y equals 1. All right, so let's go ahead and graph. Oh, actually, we're not done yet. This is the inverse, right? This is the inverse right here. So to get the original, you need to switch all the x and y terms, right? So switch x's and y's. So 1 and 1/4 is the x. Let's see, 1 1/2, 2, 3, 5. And then on the y's, I'm going to get 0, 1, 2, 3, 4. And if I switch the x's and y's, then the range of the inverse becomes the domain of the original. The domain here becomes the range. So now the range is all real numbers. And the asymptote, instead of being y equals 1, becomes x equals 1. Oops. So now we can graph this. So I'll scroll over a little bit. So let's see, x equals 1. Let me make tick marks first. So let's see, I got to go up to 5. 1, 2, 3, 4, 5. And I go up 4, 1, 2, 3, 4. So x equals 1 looks like this. So there's my asymptote, x equals 1. Let's see, when x is 1 1/4, y is 0, so that's about there. When x is 1 1/2, y is 1. When x is 2, y is 2. When x is 3, y is 3. And when x is 5, y is 4. And you can kind of tell this thing is going to have to hug the asymptote and then curve off to the right like this. Okay. All right, so I hope that helps a little bit. And then we already have domain range asymptote info right there anyway. Okay. So that's graphing a log function. The way that we did it, again, we found the inverse, which is an exponential, which we know how to graph. We come up with the charts for the inverse, and then at the end, you just switch all the x's and y's, switch the domain and range. Okay, so let's take a look at the next one. So these are evaluating a couple of logs. Now, this one doesn't have a base listed, but remember, if there's no base listed, that's the same thing as base 10. And it's 10,000 there. So what I can do is I can say, well, 10,000 is really 10 to the 4th. And you might remember that if you have log base b of m to some power, you're allowed to bring that power down in front, and it becomes p log base b of m. So this 4 can come down in front, and you've got 4 times log base 10 of 10. And then you might also remember, if these guys are the same, the base and the thing inside, that's 1. So this whole thing turns into 4 times 1, which equals 4. Okay, let's take a look at the next one. The next one, you got to use a little bit more manipulation for it. So for the next one, okay, sorry. For the next one, one thing you can do, and you could have done it for A also, is set this thing equal to x, right? If you don't immediately see how to do it, just set it equal to x. And so then you can use that conversion formula. Log base b of a equals c turns into b to the c equals a. So in this case, well, the b is 36. So 36 to the c, which is what the log equals. So 36 to the x equals a, which is root 6. Okay, and when you look at this, you might be able to tell, well, 6 sort of seems to be an important number involved here, because 36 is 6 squared. So that's, the 36 to the x is really 6 squared to the x. And root 6 is the same thing as 6 to the 1/2. So then you got a power to a power, you can just multiply the powers. And I've got 6 to the 2x equals 6 to the half. Well, that means that 2x has to equal 1/2. And then if I divide both sides by 2, or multiply both sides by another half, let's say, then I'm going to get x equals 1/4. Well, that means that the original problem, which I set equal to x, is going to be log base 36 of root 6. We know that that's now 1/4. So there's my answer, 1/4. All right. And you could have done this problem the same way. If I'd done that, it'd be log 10,000 equals x. Call that base 10. And then if you convert it, you get 10 to the x equals 10,000. And then you can figure out, okay, well, that means x is 4, so the original problem, the answer is 4. All right. Okay, down here, expand. So you might remember the rule. If you have log base b of m times n, that actually, if you wanted to expand it, it'd be log base b of m plus log base b of n. And if it was m divided by n inside there, then there'd be an m here minus the n there, right? So let's take a look at this one. So expand ln. Now remember, ln is the same thing as log base e. And then I've got x squared root e inside there. Okay, so if you think of it as x squared times root e, then this is going to turn into log base e of x squared plus log base e of root e. Okay, so we can do a couple of things. That square can come down in front, right? So then this is going to turn into 2 log base e of x. And then over here, root e can be written as e to the 1/2. And then I can bring that 1/2 down in front. So this one over here, 2 log base e of x, can't really do anything else with that, plus 1/2 log base e of e. Well, log with a base and the actual thing you're plugging in the log are the same. So this is 1. So then this turns into 2 log base e of x plus just a regular old 1/2 times 1, which is a 1/2. And then if you wanted to, you could switch that log base e back into ln and then plus the regular 1/2 there. Okay, so there's a few more log and exponential type review problems. Hope that helps a little bit. All right.